So last time, good morning everyone. So last time we talked about probability of event relations and we already covered up until conditional probability. Okay, so if you don't remember what that is, let's go over it a little bit. So conditional probability means that they're asking you P diameter okay given that it is too short. So that given that it is too short reduces the sample space. Let me write that down somewhere. So P, if you have any questions, you can interrupt me. P of diameter okay. You want to find diameter okay, but at the same time, you already have an info. This thing, you mention it as given. Okay, what is the probability that you select an aluminum rod with a diameter that is okay, given it is too thin? Okay, so I already told you guys, this thing is the limiting factor or the limiting parameter. When you have something that is given to you, the sample space is reduced. And someone got this wrong as well on the quiz, even though I already emphasized it many, many times in class. Okay, so again, when you have this statement or this term, the probability of you selecting an aluminum rod with a diameter that is okay, given that it is too thin, the parameter that limits your sample space is the second term, always the second one, not the first one. So let's say this is my sample space and I have like 1,000 outcome. Yes.
We can see only the first slide.
But I'm already scribbling. Can you see my scribbles?
No.
No. Oh my God. Okay. Thank you for informing me. Let me share again. Stop sharing. Can you see now?
Yes, doctor. Yes, doctor.
Yes, doctor, again.
All right. Okay, I'm still recording. Sorry about that. Okay, so let me repeat this part over here. When they ask you the probability of an aluminum rod that has a diameter that is okay, given, when you have this bar over here, you mention it as given, and this is the info that you have already. Find the probability that the aluminum rod has a diameter that is okay, given that it is too thin. The too thin limits your sample space. Now, for example, your sample space is inside this box and you have 1,000 outcomes. Now, within this 1,000 outcomes, you have to only select those that are too thin. So anything within this circle is too thin. This is your given info. And now I want to know what is the probability that the diameter is okay, given that it is too thin. Now let's say the event that the diameter okay is over here. So only this part overlaps with too thin. Therefore, only this guy is your probability. Okay, it has to overlap. It's almost like intersect, but in this case, we say that the too thin is your limiting, the parameter that limits your sample space. So that is your conditional probability. That's just a recap. Okay, so let me remove this. This probability is called, conditional probability and independence, a population of 1,000, this one, okay. 9 to 8 meet this diameter specification. Yeah, we already did this one. Conditional reduce sample space. Okay, this one already did. Not this one. We already did this one as well. Okay, so the conditional probability equation is P, probability of A given B is equal to probability of A intersect with B, or probability of A and B. Okay, this guy means and, over the probability of B. So this is your equation. Now, what if you already have this guy and you have this guy, but you want to find P probability of A intersecting with B, what do? You already have these two information. How can you find probability A intersect with B? Can we manipulate this equation? Everyone's clueless? Yes, we can multiply it. So it's just like regular math. Don't be scared of statistics. So it's just like regular math. PA given B, PA intersect B. Now I want to get rid of this probability B because I just want this as my subject, right? I'm trying to find this guy over here. So what do? Wait, I need to put this over here first. I want to get rid of probability B. So what do? I multiply with probability B. Why is my handwriting so bad? I need to make this nicer. Okay, give me a minute. Where's my pen? Oh my God. Let me rewrite this. Okay, so probability of A given B and probability of A intersect with B over probability of B. Let's say I have probability of B equals to 0.1. The question gives me this value, and probability of A given B, they already give me this answer. Maybe it's 0.05. Now they ask me, hey, what is the probability of A intersecting with B? No, so the way I can do this is I can substitute the numbers here, or I can ignore this first. And what do? Is I multiply both sides with probability of B. When I do that, I am crossing this out. So I'm left with probability of A intersect with B. This is my subject now because this is what I want to find. So what do? Is I multiply probability of B with probability of A given B, which are these two guys over here. 0.1 times 0.05, whatever that is, that's your answer. Okay, so that's another way to manipulate this equation. And the same case goes, you already have this value, you already have this value, you want to find what is the probability of B. So it's the same way. You shift it, you multiply, and you manipulate this equation to get probability of B as your subject. So let's try to do that. This is fairly easy. I'm just showing it to people who don't find this easy. Bear with me. So I'm bringing this over here, and what I'm left with is P A given B. Okay, so whatever the value is, so P intersect with B, sorry, P A intersect B is whatever that the question gives you. Let's say it's 0.5 and PA given B is 0.05. This is just an example. Okay, so you can find what is the probability of B just from this equation. So you need to memorize this equation. Okay, I know math is like not supposed to memorize things, but statistics you have to. Okay, let's talk about conditional probability again, another example. So let's say you have the probability for, what are we talking about here? Floor on top, floor on side. Let's say we're talking about a can. Okay, we have a can. It's a very nice can, and there's a factory that produces this can. But of course, with everything, there's sometimes you produce something with flaws, right? And not everyone is perfect. Okay, so this factory produces cans. There is a probability that there is a flaw on the top of this can. The probability is 0.03. The probability that this can has a flaw on the side over here, 0.02. And the probability of the can having both flaws on the side and on the top is 0.01. Question number 1, find the probability of flaw on top given that the flaw is on the side. Which one limits the sample space? Which parameter limits the sample space? For question number 1, anyone?
Flaw on side.
Flaw on the side. Okay, so for question number 2, it's find probability flaw on the side given flaw, I'm pronouncing that, flaw on the top. So based on your friend's answer, I would say the flaw on the top is my limiting parameter that limits the sample space. Now my question to you is this answer the same or is it not the same? Should we find out?
Not the same.
Not the same. Okay, anyone feels like it's going to be the same? Okay, I want to bet. No, don't bet. I want to guess that it's going to be the same. So let's see. Okay. So let's see if question 1 and question 2 will give us the same answer. Okay, so let's use this equation that we already learned about conditional probability, right? So given find P flaw on top, given flaw on the side. So this, my equation will be P flaw on top given flaw, flaw on top, given flaw on the side. Okay, panjang pula. Okay, and then this is going to be equal P probability of A intersect with B, which means that it is probability of flaw on top. Let's just call it FOT, FOS. Okay, that's going to make my life easy. FOT, FOS. Let me write that. FOT, FOS. Okay, so FOT intersect with FOS over probability of B, which is this side, flaw on side, FOS. Okay, so this is question number 1. Okay, question number 2, flaw, I'm supposed to use the acronym, flaw on side, which is FOS, given FOT, the flaw on the top, and this is going to be equal to FOS intersect with FOT over probability of FOT. Okay, just by looking at this equation that I already put in the parameters, I know that, okay, this side, the denominator is obviously not the same. So your friend is probably right. What about P intersect with probability of FOT intersect with FOS? Is this guy the same or not the same?
Same.
It's the same value, right? Supposedly it's supposed to be the same value. So the only difference here is the denominator. Okay, so it's very, very important for you to identify which one is the limiting factor, because your limiting factor is your denominator. Okay, limiting factor is B, denominator is also B. Okay, so let's try to solve it. Flaw on top, I'm going to use a different color for this one, green. Flaw on top is 0.03, flaw on side is 0.02, flaw on side and flaw on top, which means that this is intersect. So this is going to be 0.01 over flaw on side, 0.02. And for this guy over here, this one is the same, 0.01. Okay, and flaw on top is 0.03. So it's not the same. So your friend is correct and I am wrong. Okay, so this is the answer. Use your calculator. Okay, so in most cases, not all cases, most cases, probability of A given B is not the same as probability of B given A. Okay, and we already proved that. Okay, so enough with conditional probability. Now we're going to talk about independent events. Independent events. Independent means that they don't depend on each other. So sometimes the knowledge that one event has occurred does not change the probability that another event has occurred. So what does that mean? In this case, conditional and unconditional probabilities are the same. Meaning to say, even if you have an info, let's say we're talking about the probability of the diameter being okay, given it is too thin, knowing that it is too thin doesn't change the probability. So the conditional and unconditional is just the same. So let's see how that is. So here we're talking about probability that is too long. So the probability that the probability that the length is too long should be over here, right? Out of the sample space is 1,000. I think we're still talking about the aluminum rods here. So 1,000 aluminum rods, the sample space is 1,000. I want to find out what is the probability that the aluminum rod that I select is too long. Okay, so 2 plus 25 plus 13 over 1,000. So that is 3840. That is going to be 40 over 1,000. Now, this is a unconditional probability because it is based off the entire sample space. Remember the definition? Unconditional probability is based off the entire sample space. For conditional probability, the sample space is reduced. Okay, so this is unconditional. Okay, I hope you can understand my handwriting. And then now we have to find out what is the probability that it is too long given that it is too thin. And they already put the equation here for us. We just have to put the values inside. So P too long and too thin. What is the probability? P that is too long and also too thin is just 2 out of the 1,000 samples. And then probability of too thin. Probability of too thin is this guy over here. 10 plus 38 plus 2. So it is 50 out of the 1,000 samples. So am I doing this correctly? Anyone know? Anyone has any objections? So everyone's okay. Does anyone have any questions?
No, Doctor.
Okay, independent events. Let me just this one, this one. Okay, and too thin. Okay. So the answer here is we can just cancel this out. So I get 2 over 50, which is 0.04. 0.04. What about this one? 20 divided by 1,000. Also 0.04. So the answer is the same. Even though this guy is conditional probability. We have this guy over here, which means that it is conditional. Therefore, these the too long and too thin are independent events. Too long and too thin are independent events. Because even though I know that the sample space is reduced by too thin, it didn't affect my answer at all. The answer was the same as if it is the probability from the entire sample space, which is 0.04. Okay, so with that said, we know that these two events, too long and too thin events, are independent of each other. Okay, but it does not mean that the other parameters are also independent, just for these two. Okay, if we can prove it that they are independent, then yes, these two events are independent of each other. Okay, so in this case, the conditional and unconditional probabilities are the same and the events are said to be independent. So this is a definition. Two events A and B are independent if the probability remains the same, whether or not the other occurs. Okay, so it is in symbols, considering probability of A is not equal to 0, which means that there is a probability of it occurring, and probability of B occurs, which means that it is not equal to 0, then A and B are independent if probability of B given A is PB, or equivalently probability of A given B is PA. Meaning to say this info over here does not affect probability of B. This info over here does not affect the probability of A. It's still the same probability as if we are talking about the entire sample space. Okay, if either the probability of A is equal to 0 or PB is equal to 0, then A and B are independent. Let's say you have two events, right? You have event A and event B, and you want to find out what is event A. And you found out that probability of B is equal to 0. So probability of B does not ever happen, which means that probability of A given B is obviously just probability of A. Okay, so that is your like a shortcut. Okay, but I think that's common sense. If the other event does not occur, then there's no limiting factor, right? The sample space is not reduced. Okay, so I hope everyone got that. The multiplication rule. Sometimes we know the probability of A given B and we wish to find probability of A intersecting with B. We already discussed this. What do? We just multiply both sides with the probability of B. This is what they have over here. I'm just recapping this part. If A and B are two events, right? And you want to know what is probability of A intersecting with B. Now using the equation of conditional probability, so this is P intersect with B over P of B. This is your limiting factor. You want to find out this side over here. What do? You multiply both sides of the equation with probability of B, and you get the P intersect with B. So PA intersect with B. The reduced sample space cannot be 0. Now imagine if your probability of B is equal to 0. The equation will not hold. So you cannot do the multiplication rule if your event does not happen. Okay, this is what they are saying. So if your probability of B is 0, then if you multiply it here, first of all, this guy will become infinity, which does not make sense. And if you try to move it around, this guy will become 0, which also does not make sense, considering we have a question asking for it. So the multiplication rule does not hold if one of the events is 0, okay? Okay, so when two events are independent, so this is a lot of like statements or definitions that you have to remember. When two events are independent, like they are mutually exclusive, then probability of A given B is equal to probability of A. Remember, this guy is no longer limiting your sample space because it does not affect the probability of A occurring. In same case over here. So the multiplication rule simplifies to this guy over here. And we have seen this for mutually exclusive events in module number 3. Okay, mutually exclusive. If A and B do not overlap in the sample space, they are independent events. If I wanted to find out what is P intersect with B, I just multiply the two. PA multiply with PB. Okay, so this result can be extended to any number of events. Let's say you have more than two. You have A, B, C, D. So they are, oops, that one is overlapping, so it's not mutually exclusive. So this is D, A, B, C, D. They are all mutually exclusive or they are all independent of each other, meaning to say I want to find out what is probability of A occurring given D is still PA. I want to find out what is the probability of C given B. It is still probability of C because they don't overlap. They don't affect my other events. So what if I wanted to know what is PA intersect B intersect C intersect D? So I just multiply all of these events together, the probability of them. Yes, any questions? No questions? Okay. If I'm going too fast, you can tell me. Okay, example, a system contains two components, A and B. Okay, so both components must function for the system to work. So we have two components. Yes? Is there any question? Saravana, do you have any questions? No, okay. So I'm going to mute you, okay? Mute. Steve is also not muted. I can't seem to mute Saravana. Wow. Saravana is kebal. Itu tak boleh mute dia. Okay, never mind. Okay, the multiplication rule, the system contains two components, A and B. Both components must function for the system to work. The probability that component A fails is 0.08. Okay, so we want them to work, but they're giving us the probability for component A to fail. And the probability that component B fails is 0.05. Assume the two components function independently. So we have two independent events, right? So what is the probability that the system functions? So how do we find out? So both components must function. So it cannot be A works and B doesn't work, or A works, B doesn't work. Both have to work. So A must work together with B. So we need to find what is P intersect with B. So how do we find this one? They are independent events. What is the equation that we need to use? We just talked about it in previous slide. If I have two independent events, what equation should I use?
Multiplication.
Multiplication of? Okay, let's not talk about the numbers yet. What should I multiply over here? The probability of A failing or the probability that A works?
A works.
A works with? Okay, so I'm going to put W here. And of course, you also want the other component to work as well, because we want to find out what is the probability of the system working, right? For the system to work, both components have to work or they cannot fail. So I need to find out what is the probability that A works and multiply that with the probability of B works. Now, I already simplified this. What is the next step? Work, and should I call someone? We're just applying the equation. It's really not hard. The equation that I talked about previous slide. I'm not gonna test you guys on things that are far behind. It's just the previous slide. Okay, so B work. Okay, so we want to know, this is so terrible. I need to write this nicely. Intersect B work. Okay, that's my best handwriting. So probability of A work intersect with B work. They both have to work. They both have to work. If I put it like this, A work union or B work, it means that either A works or either B works or both can work. So it's just one or the other or both. So this is not what I want. I want both of them to work so my system can function. So this does not apply. So A intersect with B, both are independent events. Now look back at the equation that we talked about just now. If we want to know what is the intersect of A with B, We multiply them given that they are mutually exclusive events or independent events. They are independent, right? So we just multiply. PA works with PB works. Now, how do I find out how the probability of A working, given that I know what probability of A fails?
1 minus 0.08.
Yes, 1 minus 0.08. We find the complement of the event. You have your sample space, right? You know that this is 0.08. This is the event that it fails. What is the event that it doesn't fail? It is this entire sample space. So it's just 1 minus 0.08. Okay. So that is, and then probability of B is the same way over here. It's 1 minus with 0.05. So this is how you find out the probability. So the probability that the system functions is 1 minus 0.08. That is your 0.92. One minus 0.05. Okay, 0.95. So let's see the solution. Oh, I didn't put the solution. Let's see. Answer is 0.874. 0.92. 0.874. Whoops, 0.874. Okay, so that's your answer. Everyone okay with this?
Betul.
Yes.
Kalau contoh kalau apa ni, saya multiply the probability of it fails and then minus by 1.
The probability of it fails and then minus by 1.
Yeah. Or will it not be correct? 0.08 and time 0.05 and then you do tolak by 1.
Okay. When I use this approach, I'm assuming that they are not in the same sample space. Let's see. 0.08, 0.05. Okay. And then this one doesn't give us the same answer. This assumption tells me that component A is a sample space of its own and component B is a sample space of its own. Because when I talk about this guy, because they are independent, right? They are independent. I'm gonna have to look back on that one. Why doesn't it work? That's a good question, actually. Let me highlight that. Why can't, that's not a can't, it's a can't. Why can't we multiply A fail with B fail? So this is the question. I don't know who asked. I think it was Haris, not sure. So he's asking, yes, okay. So why can't we multiply probability of A failing with probability of B failing and then 1 minus that, because that is also a complement, right? I'm not sure. I have to get back to you guys on that one. So that's a good question. We need to know which works and which doesn't work, right? Okay, so let's highlight this first. Next question. Of the microprocessors manufactured by a certain process, 20% are defective or 0.2. Okay, are defective. 5 microprocessors are chosen at random. Okay, assume they function independently. So they are independent events. What is the probability that they all work? Okay, so remember, if we have like A, B, C, D events, and they are all independent, how do you find out that they all work? So A work, intersect with B work, intersect with C work, intersect with D work, right? So this is how you find it. Now in this case, we have 5 microprocessors. So how do we do this one? I'll give you guys 2 minutes. So what's the answer? So it's the same approach as the previous one. Previous one was 1 minus 0.08, right? Which means that you are finding the complement of it failing, which means that you're finding when it works. And of course, the same thing over here. But here, 5 microprocessors all have the same probability of being defective is 0.2. So if I wanted to know microprocessors, let's call it M1 intersect with M2, intersect with M3, intersect with M4, intersect with M5, this is going to be equal to 1 minus 0.2. This is the probability that it is not defective. And I multiply this 5 times, which means that I can just put this to the power of 5. This will be my answer. I don't know if this is correct. Let's see. 1 minus 0.2 to the power of 5. So the answer should be 0.328, sorry. And let's see if it's the same as textbook. Yes, the answer is 0.328. So we use the same approach, 1 minus the probability of it failing, and you just multiply it as many times as the events, okay? And of course, the same question applies to this guy as well. Why can't we multiply 0.2 to the 5 and then 1 minus that? So we'll answer that in later class, okay? Okay, so toss a fair. So, okay, I'm gonna leave you guys to this exercise yourself and this one as well. The solution is there, just go over it. And finally, let's summarize what we have learned for this module. So the summary for probability rules is when we're talking about the probability of probability of A or B, or you can say probability of A union with B, it is equal to probability of A plus probability of B minus probability of A intersect with B. I don't know if you guys still remember this. Very, very important equation. You need to remember it. But when 2 events A and B are mutually exclusive, meaning to say they don't overlap, therefore probability of A intersect with B is equal to 0. Therefore, probability of A probability of A or B is equal to the addition of these 2 guys. Only for this equation, okay? And then when we're talking about complement, we say it like this: 1 minus probability of A failing, or probability of. This is the same example as the microprocessors. You use the complement. Okay, and then when we talked about conditional probability, which is probability of A given B, this guy reduces the sample space, and the top part is your probability of A intersect with B if probability of B does not equal to 0. Okay, so this equation applies only if event B happens. So 2 events A and B are independent if and only if probability of A given B is equal to probability of A, and probability of B given A is just probability of B, meaning to say that the limiting parameter does not affect the probability. Otherwise, they are dependent. So if the events A and B are independent, then probability of A with and B is probability of A multiplied with B. Okay, so that is the end of this module. So moving on, I'm going to give everyone 5-minute break and then we're going to continue. We have 5-minute break is 10:27. Okay, let's come back. If you have any questions, you can ask me. Okay, half an hour to go. We're going to end at 11. One more minute. mutually exclusive. Then. Okay, is everyone here? I have something very important to say about difference between mutually exclusive and independent. I shouldn't have used the term lightly. Okay, so I need to go back to the previous module. Open recent. Okay, I want everyone to focus here and please take note of what I'm going to say here. So there is a difference between mutually exclusive events versus independent events. I used the term like I flipped the terms around and that was wrong of me. They are not the same. When we talk about mutually exclusive, okay, the events cannot occur at the same time. They cannot. Events cannot occur at the same time, which is why, let me finish writing this. My limiting factor is my handwriting, so it reduces my sample space of performance. Okay, mutually exclusive is when events cannot occur at the same time. This is why when we talked about P, probability of A union with B, and this is the equation, and if they said that if the events are mutually exclusive, this guy becomes 0. Now, this is not the same case as when the events are independent. When the events are independent, this is the equation. So they are not the same. Now, what is independent events then? Independent events is when events both occur at the same time, but they are not affected by each other. So it's hard to describe it in the sample space. Independent events that can occur at the same time but not affected by each other. By each other. I should have typed that. Why did I bother writing it? Okay, so these are the two differences and their equation are also different. Mutually exclusive events, the probability of A intersect with B is 0. Whereas for independent, probability of A intersecting with B is the multiplication of those probabilities. Probability of A multiplied with probability of B. Now let me try finding a Venn diagram that describes the difference between these two guys. Now we know that mutually exclusive event in a sample space looks like this, right? In this event is A and this is event B. And there's basically no overlap between them, which is why P A intersect with B is just equal to 0. This is an A. Okay, so independent event, I can't find the Venn diagram. So I don't know how we can describe this. Give me a minute. Hopefully everyone can have a good understanding of these two concepts. So I also don't know what the Venn diagram looks like. I need to find it. It's not in the textbook, at least. Okay, so that's another thing that I need to find. So this is the Venn diagram for mutually exclusive event, and I still owe you guys independent event, okay? So I hope that is okay for everyone. Don't get confused. Okay, mutually, now we're going to this one, module number 5. Any questions? before we continue with this one? No questions? Okay, so I'm going to continue. Yes.
No question.
Oh, no questions. Okay. I was excited to answer. Okay, never mind. Let's continue. Okay, so we have a lot here. So let's take a deep breath and try to read this. Suppose that an electrical engineer, we're not electrical engineers, we're communication engineers, has on hand 3 10-ohm resistors and 3 20-ohm resistors.
Sorry, Doctor.
Yes?
Sekarang kita orang tengok summary of probability dulu lagi, slide.
Nak tengok summary of probability balik?
Bukan. Doktor dah pergi slide lain ke?
Oh, tak tukar lagi. Okay. Okay, can you see it now?
Yes, Doctor.
Okay, oh my God. Don't know what is wrong with the PowerPoint today. Okay, so we're talking about random variables now. We have half an hour to go. Let's do this. Suppose an electrical engineer has on hand 3 10-ohm resistors. Okay, so he has 3. This is very cute looking resistor. And 3 20 ohm. So this is 10 ohm. And we have another 20 ohm. I know resistors don't look like that. Okay, so he wants to connect these resistors in series to create 30 ohm. So he takes one of 10 ohm, connect it with the 20 ohm to make 30 ohm. Of course, this doesn't look like resistors. Okay, now suppose that in fact the 3 resistors labeled 10 ohm have actual resistance of 9, 10, and 11. Let's write this down. It's too thick. 9, 10, and 11. And the other 3 for the 20 ohm is 19, 20, and 21. So they don't have the exact value of 20. Okay, so the engineer in this experiment wants the sum of the 2 resistance rather than their individual values. Therefore, we assign to each outcome a number equal to the sum of the 2 resistances selected. Okay, so let's go back. We have 3 10 ohm resistors, 3 20 ohm resistors, and the engineer wants to select 2, only 2, because he wants to create 10 and 20 to have a resistance of 30 ohms. So he has to pick one of 10 ohm, one of 20 ohm. So the outcome in our sample space, if I were to list this down, would be 9, 19, 9, 20, sample space, 9, 21. 10, 19, 10, 20, 10, 21. This is my sample space, not done yet. Okay. Then we have 11, 19, 11, 21, 11. This is 20, this is 21. So I have to list all the pairs that is possible. All the pairs that is possible for the engineer to pick is my outcome. And this makes up my sample space. I know we've learned about this. I'm just repeating myself here for those who don't get it yet. Okay, so this is my sample space, and this is my outcome. Okay, so now the engineer doesn't really care about this pair. He wants to know if this outcome of the pair gives him a 30 ohm or not. So now I put this in a table and I make another column because I want to know what is the summation of these 2 resistors. So this becomes 19 and 9 is 28. Then this is 29 and this is 30. This is 29 and this is 30 and this is 31. What is this? This is 30 and this is 31 and this is 32. This is the sum that the engineer cares about. He doesn't care about the pair, even though we list it as our outcome because it is the outcome. He cares about the sum and we call this as capital X. This capital X assigns a real number to our outcome. Our outcome is a pair. It's not a real number. We are assigning a real number to this outcome. This is known as random variable. X is our random variable. This is a new term. we are assigning a real number to our outcome. Our outcome does not necessarily have to be a number. Sometimes we put a car, no car. Let's say the outcome is 1. The X is 1. So you are assigning a real number to an outcome that can be anything, right? Okay, so this is called the random variable. So a random variable assigns a numerical value to each outcome in a sample space. Now here they also listed the probability of the pair being chosen. Since we have 9 possible pairs in the sample space, therefore selecting one pair would give us a probability of 1/9, and all of them give us 1/9. Okay. Any questions about this example? Does everyone understand what random variable is? Everyone okay? Okay or not?
Okay.
Okay. Moving on. Now the
Okay,
function x. Okay, all right, thank you. So the function x, capital X, which assigns a numerical value to each outcome in the sample space, is the random variable. We talked about this. Now the question is, list the possible values of the random variable x. Okay, list the possible values of random variable x and find the probability of each of them. Now we already listed it out up here in the previous slide. What are the possible values? It's 28, 29, 30, 31, 32. So it's 28 up to 32. So the list of possible values is 28. I should just copy this guy. Let's copy you. Copy. And does this work? No. Okay. Okay, better. So this is our random variable. The possible values for x is 29, 30, 31, and 32. Now they're asking us, okay, this is the possible values. We answered this first part of the question. The second question is find the probability for each of them. Now, when we talk about the 1/9 here, this is not the probability for the random variable. Now, as you can see here, we have redundant values for the random variable, which means that we can combine these two guys together and these two guys together. Sorry, 3 guys and these two. So 29 has 2 pairs. So 28, the random variable 28 has a probability of 1/9. Let's see, this is P over X, okay? And the probability of random variable 29 is 2/9. I'm just adding them together, 1/9 plus 1/9. And then for 30, 1, 2, 3, 3/9. This is a 9, not a 1. Okay, and then 31 happens 2 times, 2/9. This is a 9, and 32 happens once. So this is the probability for each of the random variable. Which brings us to our next term. This is not done for fun. So. Okay, I should do this later. Let me just say that this guy is called the probability. Let me type that. Probability mass function. This is known as the probability mass function. Okay, so we're going to learn about this one as well later. Probability mass function is also known as probability distribution. If you are more familiar with the probability distribution term, it is the same thing. It is a random variable and it tells you the probability of a random variable occurring. Okay. Moving on. So before we dive deeper into random variables, we need to know that there are 2 types of random variables, which is discrete sample space and also continuous sample space. The random variable comes from a discrete sample space and comes from a continuous sample space. The one that we talked about, it was a discrete sample space. The one that we talked about here in this table is called the discrete sample space. And we're going to discuss why that is. Okay, so discrete sample space, possible values form a discrete set. Values can be ordered and there are gaps between the adjacent values. For example, when we're talking about 28, 29, 30, 31, the gap is in between 28 and 29. I don't consider 28, why can't I draw? I don't consider 28.1 as my outcome. Why not? Because it's a discrete sample space. I don't consider 28.999 as my outcome because this is a discrete sample space. So the gap between 28 to 29, there is a gap, which is the values here. I don't consider it. So there is a gap. Whenever we have gaps in between our outcomes or in between our random variables, it is a discrete random variable, or our sample space is discrete. For example, cases where we have discrete sample space is the number of defectives in a sample of key items. We talked about the can having flaws. How many cans have flaws? So that is discrete. You only have integers. Is it either 1 can? Is it 2 can? Is it 3 can? You can't have 2.5 cans are defective. Doesn't work that way. You only have integers. So that is a discrete sample space. Another one is the number of highway fatalities per year in a given state. Let's say there are 10 accidents on the road. You don't say, oh, there are 9.5 accidents on the road. It doesn't work that way, right? You only have to specify integers. So that is discrete sample space. Now, continuous sample space, on the other hand, the possible values contain an interval. For example, I'm talking about an interval of A to B. Let's say A is 29 and B is 30. Very small interval. So anything within 29 and 30, 29.1111, 29.1112, 29.1113, all of the values between 29 and 30 is a possible outcome. So that's tough. So this is why we go with discrete sample space first. So continuous sample space is all the values, there's no gap. Values are all the points between some two numbers. For example, we're talking about 28 to 31. This is our interval, which includes 28.1, 28.2, 28.3, 28.5, 28.9999, 29.999. So all of those values are possible outcomes. An example of a sample space of continuous sample space is possible heights, weights, temperatures, distance, and life periods. Life periods? What's life periods? I think it's just the number of, let's just ignore this one. Not sure what that means. Okay, so possible heights, weights, temperatures, distance. So let's say you want to measure a distance from this book to my bed over there. The distance is 20.122. And if I move the bed a little bit further, it's 21.123. So anything is possible within that interval. Okay. So exercise, identify whether the set of outcomes are discrete or continuous. So number one, the number of packets that arrive to the destination. Is this discrete or continuous? Are you familiar with packets or not yet?
Not yet.
Oh, not yet. Okay. So this is discrete, right? Because packet is only like 1 or 2 or 3 or 4. You can't have 2.5 packets. Let's just consider this like Maggie packets. So you can't have like, I want to give you 1.5 packets of Maggie. It doesn't work that way. So packet it needs to be integers, okay? Number 2, the waiting time of a customer in queue. So time is continuous or discrete?
Continuous, Doctor.
Continuous.
What about the number of cars?
Discrete.
Discrete. Okay, and number of students that succeed in an exam?
Discrete.
Discrete.
I cannot say 2.5 students passed my exam, so only half of the body is passing the exam. This doesn't make sense. Okay, moving on. Good. So exercise. Computer chips often contain, what time is it? Computer chips often contain surface imperfections. Okay, I hope I don't get one. For a certain type of computer chip, 9% contains no imperfection. Great. 22% contains 1. 26% contains 2 imperfections, and 20% contains 3 imperfections. And you can read it yourself. Okay, 11 contains 5. Let Y represent the number of imperfections in a randomly chosen chip. You choose one, you only choose one here. Your outcome is just one chip. So let Y represent the number of imperfections. So number of imperfections, we can say Y is equal to 0, 1, 2, 3, 4, 5. What is Y? What do we call Y? What is Y? What is the term for Y? Is it probability mass distribution? Probability mass function? Is it discrete function? What is it called? You guys already forgot? It's random variable. Random variable. Remember, random variable assigns a real number to our outcome, no matter what the outcome is. So here, even though it looks straightforward, it is still a random variable. Just now we had to add the two resistors together. Here we don't have to add, we're just assigning a number immediately. Okay, so that works as well. Even though the outcome is the same as the random variable, it can work like that as well. So what are the possible values of Y? It is 0, 1, 2, 3, 4, 5. Is Y discrete or continuous? Now this is an easy question. Discrete or continuous? Is it continuous? Discrete? Anyone? I think everyone's tired. Come on guys, 10 more minutes. Discrete or continuous?
Discrete.
Discrete, because what's the justification for that?
Because the imperfections can only be integer. There's no like 1.2 imperfections.
Correct, because we're talking about integer. The number of flaws is in integers, correct. Okay, find the probability of Y random variable equals to Y for each possible value of Y. So now they're asking us to list down the probability of, oops. Okay, probability of Y equals to small y. So this is listing the probability. So for random variable 0, there is 9%. So this is going to be 0.09. And for 1, it is 22%. For 2, it is 26%. Okay, for 3, it is 0.2%. Sorry, 20%. Number 4 is 12, 0.12. And number 5 is 0.11. Okay, so that is it. That's the answer. So this is the solution. The random variable Y is discrete because it takes only integer values, as your friend mentioned. And this is the probability for each of the random variable. So random variable is discrete if its possible values form a discrete set. This means that if the possible values are arranged in order, there is a gap, meaning to say there's no, the value needs to be whole. The set of possible values may be infinite. It can be very, very big. For example, the set of all integers and the set of all positive integers are both discrete set, even though we're talking about the numbers, the interval between minus infinity to infinity. But if we specify that the number should only be integers, that set is still a discrete set. Okay, even though the number reaches up to infinity. Okay. So The list of possible values 0, 1, 2, 3, 4, 5. This is your random variable along with probabilities of each. Provide a complete description of the population from which Y is drawn. Drawn from a population or a sample set. From a sample set. Okay, so here, if we add these probabilities all together, we should get the probability equal to 1. Okay, so this, when you have a probability, when you have a complete list of probability for the random variable, you have a probability mass function. It has to be complete. Let's say you get rid of this. Therefore, your the total probability is less than 1, right? So this is no longer your probability mass function. It's just a list of probability. But if you have a complete set, then yes, it's called a probability mass function. Now, why is it important for us to know what is the probability mass function? Because typically when we want to visualize data, we want to plot it into graphs. For example, we have these values, and these values, probability values, make up equal to 1, which means that this is a complete set of probability mass function. So if we were to plot this into a graph, we plot it discretely. For example, this is the number of flaws. The number of flaws is 0, number of flaws is 1, 2, and 3. And the y-axis tells us the probability. So this is 0.48, this is 0.39, and this is 0.12, and this is 0.01. So this is how you plot a discrete probability mass function. It is also called discrete probability distribution. Okay. So I'm going to continue on this topic next class, which is tomorrow. Tomorrow is going to be 9 a.m., not 9:30. Okay, so I'll see you guys tomorrow. If you have any questions, you can ask me. If not, have a great rest of the day. If you're having lunch, have a great lunch.
Thank you, Doctor.
Welcome.
Thank you, Doc.
Thank you, Doctor.
Thank you, Doctor.
Welcome. Bye-bye.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.
Thank you,
Thank you,
Doctor.
Doctor.
Bye-bye.